Welcome. In this video series, we'll be diving into one of the most popular resources for aspiring software engineers called Cracking the Coding Interview by Gail Lackman McDowell. So, whether you are preparing for a technical interview or you just want to brush up your coding skills, this book is a must read. Here, I'll be giving down a summary of key questions, answers, and strategies. We will start with the chapter Arrays and Strings and go through its questions. Our first question is a classic interview problem called check permutation. In this question, given two strings, our task is to determine if one is a permutation of other. Now, before you start coding, we need to clarify the problem with the interviewer. There are a couple of important questions you should make with the interviewer. First, is the permutation case sensitive? Or should we consider white space as significant? The first solution is straightforward. We just sort both strings and compare them character by character. If they are permutations of each other, the sorted versions of strings will be identical. Now, let's look at the code. In this code, we first check if the length of two strings are same. If they are not, they cannot be permutations. Now, we simply sort both strings and compare them. If they are equal, then the strings are permutations of each other. This solution is clean and easy to understand, but sorting has a time complexity of n log n, which might not be optimal for larger strings. The second solution is much more efficient. Here, we check character counts. It is more efficient for larger strings. Here, instead of sorting, we can check if both strings have identical character counts. The idea is to count how many times each character appears in both strings and then compare these counts. Let's look at the code. To keep a count of character, we use an unordered map as to fetch anything in it will be order of one time. In this approach, we first check if the lengths are same. Then we create an unordered map to count the occurrence of each character in the first string. Next, we then decrement the counts while iterating through the second string. If any count goes below 0 or character is not found, the strings are not permutations. This method has a linear time complexity of order of n, making it more efficient than sorting. Which solution is better? First one is easier to implement, but if performance is critical, second one is better due to its order of n time complexity. We move to the next problem called contiguous sequence, finding the largest sum in an array. Our next challenge is a common problem in technical interviews, contiguous sequence. Here, given an array of integers, both positive and negative, our task is to find out a contiguous sequence in that has the largest sum, and then we have to return this largest sum. Some things to clarify with the interviewer are: if in input all numbers are negative, then what should be the output? Is it the maximum negative number, 0, or integer minimum? So, for the intuition, at first glance, you might think that including any negative numbers in a sequence would reduce the overall sum, so we should avoid them. Similarly, it seems logical to include entire positive subsequence, as breaking up these positive subsequence would give us a smaller sum. However, there are cases where including a negative number can actually lead to a higher overall sum, as in case where the combined sum of two positive subsequents separated by a negative number is greater than the negative value itself. Solution. The solution to this is found using Kadane's algorithm. The most efficient way to solve this problem is by Kadane's algorithm, which runs in order of n time. The idea here is to iterate through the array, keeping track of the maximum sum we have seen so far and the current sum of the sequence we are examining. Let's break it down with code. The first condition is put to check if the current sum is not getting negative. If it is, then we choose the next greater element and initialize the current max to it. We can go through an example walkthrough. You can pause the video and go through it and check how the algorithm works. Conclusion: Kadane's algorithm efficiently finds the maximum sum of contiguous subarray with a time complexity of order of n. Our next problem is called isUnique. The challenge here is to determine if a given string has all unique characters. In other words, we need to check if any character in the string is repeated. The first solution leverages a bit vector or an array to track the occurrences of each character. The idea is simple. As we iterate through the string, we mark each character as seen in our array. If we encounter a character that has been already marked, we immediately return false, as this means that the character is repeated. Here is the implementation of algorithm in C. In this code, we first check if the length of the string exceeds 128, as it's the number of unique ASCII characters, because in that case, it's impossible for the string to have all unique characters. We then create an array characters set of size 128 and initialize all the elements to false. As we iterate through the string, we use the character's ASCII value as an index in the array. If the value at the index is already true, we return false. Otherwise, we set it to true and continue iterating through the array. Solution 2. Without using additional data structures. An additional question that arises is, what if we are not allowed to use any data structures? We can still solve the problem, but the approach will be less efficient. The first method is a brute force order of n square algorithm, where we compare each character in the string with every other character in the string to check if it's already present. Another approach is to sort the string and then check neighboring characters. Here is an implementation of it in C. If the string has duplicates, they will now be adjacent. We then iterate through the sorted string and check if any neighboring characters are the same. If they are, we return false. The solution has a time complexity of order of n log n due to sorting step, which is more efficient than order of n square brute force approach. Both solutions have their merits. The first approach, using a bit vector or an array, is optimal with time complexity of order of n and additional space complexity of order of 1. The second approach, which avoids using any additional data structure, is less efficient but still effective, especially when space is a constraint. Always consider the constraints of the problem when choosing your solution. Palindrome permutation. Can a string be rearranged into a palindrome? Our next question, palindrome permutation. We are given a string and we need to determine if it can be rearranged to form a palindrome. We have to remember a palindrome reads the same forwards and backwards, like race car or madam. Let's explore two solutions to tackle this problem. Check character counts. Solution 1 is to check character occurrences. In the first solution, we'll count the occurrence of each character in the string. For a string to be rearranged into a palindrome, at most one character can have an odd count. This is because in a palindrome, characters need to appear in pairs, with possibly one character allowed to reappear an odd number of times, which is for the center of palindrome. Here's how you can implement this algorithm in C. In this code, we use an unordered map to count the occurrences of each character in the string. After counting, we iterate through the map to check how many characters have an odd count. If more than one character have an odd count, we return false, otherwise we return true. Solution 2. Using a bit vector. An alternate approach is to use a bit vector. Here, we can use a bit mask to keep track of which characters have been seen an odd number of times. If only one bit is set in the bit vector at the end, the string can be rearranged into a palindrome. Here's the implementation of it. In this code, we can use an integer bit vector where each bit represents a character in the alphabet. We toggle the bit corresponding to each character position in the alphabet. At the end, the bit vector should have at most one bit set to 1 for the string to be rearrangeable into a palindrome. We check this condition using bitwise operator, bit vector, and bit vector minus 1, which should be 0 if only 1 or no bits are set. Choosing the best solution. Both solutions are efficient. The first solution, using a character count, is simple and intuitive, while the bit vector approach is more memory efficient and elegant for binary operations. Choosing the approach based on the problem constraints and your familiarity with the bit manipulation is important. Our next problem is rotate matrix. We are given an n by n matrix representing an image where each pixel is 4 bytes. Our task is to rotate the image by 90 degrees clockwise. The challenge here is to do this rotation in place without using any extra space or another matrix. Let's dive into how we can achieve this. To rotate the matrix in place, we can use a layer by layer approach. Here, we'll treat the matrix as a series of concentric layers and perform the rotation on each layer individually. This method involves 4 key steps for each layer: moving the top edge to the right, moving the right edge to the bottom, moving the bottom edge to the left, and moving the left edge to the top. Here's a step-by-step guide with C++ implementation. In the C++ code, we use two nested loops. The outer loop iterates through each layer of the matrix, and the inner loop performs the rotation of current layer. We save the top element, then move the elements from the left, bottom, right edges to the new position, and finally place the saved top element to the right edge. To understand how it works, let's visualize a 3 into 3 matrix. For each layer, we take 4 elements from the top, right, bottom, left, and rotate them in place. By iterating over the matrix in layers, we ensure that every element is moved to its new position with minimal complexity. Our next problem is string rotation. Here, we are given two strings s1 and s2, and we want to determine if s2 is a rotation of s1. For example, water bottle is a rotation of ER bottle WAT. We are allowed to use only one call to a function isSubstring that check if one string is a substring of another. Here, we'll explore how we can solve this problem. Solution 1. Concatenate and check. To check if S2 is a rotation of S1, we can utilize a trick. The trick is to concatenate S1 with itself, creating a new string S1 S1. Any rotation of S1 will appear as a substring within this new string. By checking if S2 is a substring of S1 S1, we can determine if S2 is a rotation of S1. Here is how you can implement this algorithm in C++. In this implementation, we first need to check if the lengths of S1 and S2 are equal. If not, S2 cannot be rotation of S1. We then concatenate S1 with itself to form S1 S1. By calling isSubstring with S1 S1 and S2, we can verify if S2 is a substring of concatenated string. This approach has a time complexity of order of n, where n is the length of S1. Understanding the concatenation approach. The reason this works is that by concatenating S1 with itself, we create a string that contains all possible rotations of S1 as substrings. For example, if S1 is water bottle, then S1 is water bottle. Any rotation of water bottle will appear in this concatenated string. Next question is URLify, where given a string, we need to replace all spaces with %20. This is particularly useful for URL encoding. We'll solve this problem by calculating the number of spaces and modifying the string from the end to avoid overwriting characters. Solution: in-place replacement. To solve this problem in place, we first count the number of spaces in the string, then adjust the string's length to accommodate the additional characters needed for %20. Finally, we replace the spaces with %20 from the end, moving characters as necessary. Here's a C++ implementation of this approach. In this code, we first count the number of spaces in the true length of the string. We then resize the string to fit %20 replacements. Starting from the end of the true length, if it's a space, we replace space with %20, and if it's a character, we move characters to their new positions accordingly. Understanding the in-place replacement. By working from the end of the string, we avoid overwriting characters that have not yet been processed. This ensures that we correctly replace all spaces with %20 without losing any data or needing extra space. This approach efficiently handles the replacement of spaces with %20 in place with a time complexity of order of n and space complexity of order of 1. It is an effective solution for URL encoding and similar tasks. Our next problem is zero matrix. Given an m cross n matrix, if an element is 0, we need to set its entire row and column to 0. This ensures that any presence of 0 in the matrix will effectively nullify its rows and columns. We discussed two approaches to solve this problem. In the first solution, we use extra space to keep track of which rows and columns that needs to be zeroed. We'll use two additional vectors to record which rows and columns contain a 0, and after identifying these rows and columns, we'll iterate through them to set the respective rows and columns to 0. In this code, we first use two vectors to keep track of which rows and columns need to be zeroed. We then iterate over the matrix to mark these rows and columns. Finally, we zero out the identified rows and columns. Here, the time complexity is order of m cross n and space complexity is order of m plus n. To make the solution more space efficient, we can use the first row and column of the matrix to mark zeros. We'll also use two Boolean variables to track whether the first row and column themselves need to be zeroed. In this optimized solution, we use the first row and column of the matrix to mark zeros. We also use Boolean variables to check if the first row or column should be zeroed. This approach has a time complexity of m cross n and a space complexity of order of 1. One edit away, string edit distance. In this problem, we need to determine if two strings are one edit away or zero edits away from each other. An edit can be an insertion, deletion, or replacement of a character. Let's explore how to solve this problem with efficient methods. Approach. We'll look at different scenarios based on the length of the strings and determine if they are one edit away. We can break down this in three cases. Case 1. If the strings are of same length, we need to check if they differ by exactly one character. This means we can count the number of positions where characters differ. If there is exactly one difference, then the strings are one edit away. Case 2. Length difference of 1. If the length difference between the strings is exactly 1, we need to check if inserting or deleting one character from the shorter string will make it equal to the longer string. This can be achieved by iterating both strings and comparing them while allowing for one mismatch. Case 3. If the length difference is more than 1, the strings are not one edit away. This is because a single edit cannot bridge the gap of more than one character. Here's the C++ code to determine if two strings are one edit or zero edits away from each other. In this code, we first check the length difference between the strings. Depending on whether the lengths are same or differ by 1, we handle each case accordingly by comparing the strings and allowing for one edit. String compression, implementing basic compression. In this problem, we need to implement a method to compress a string using count of repeated characters. For example, the string AA, BC, CC, CC, AAA would be compressed to A2, B1, C5, A3. If the compressed string is not smaller than the original, we should return the original string. Let's dive into how we can solve this efficiently. In the basic approach, we count the occurrence of each character as we iterate through the string. If a character is repeated, we keep track of the count. When we encounter a different character, we append the current character and its count to the new string. Finally, we compare the lengths of the compressed string with the original string and return the shorter one. In the code, we iterate through the string, count occurrences of each character, and build the compressed string. We then compare the size of compressed string and the original and return the shorter one. Some conclusion and tips. Always remember to ask clarifying questions before starting your solution. Always think from a simple solution, then build up from it. Practice and revise as often as possible. Thanks for watching.